Welcome back. So last year this was split into two lessons, so that's why there's another warm-up. I'm just going to go through the warm-up with you. If you want to try it on your own first, you can pause it and try it on your own first. I just kind of want to talk you through more different approaches you can take to these problems when you're doing your homework. So we could look at cotangent. We know cotangent's odd, so the negative is going to come to the front. We also know cotangent could be rewritten as 1 over tangent x. We're going to have 1 over tangent x, and we just talked about we could pull out the negative, so we've got the negative. Cosine, I'm just going to leave the same. Cosine is even, so this negative can become a positive. Secant is even as well, because it's the opposite of cosine, so it's going to become positive, and I could rewrite it as 1 over cosine. Generally, I try to get everything in terms of cosine or sine, sometimes tangent, depends on what's useful. And then tangent is odd, so I can bring the negative to the front and just rewrite it as tangent x. So you'll notice I've got some nice things I can simplify. Cosines go, tangents go. The negatives also simplify, so we're just left with 1s. So 1 times 1 is 1. For the next one, so what I like to do is get things in terms of sine and cosine if possible. So I'm just going to start with that. So secant I'm going to rewrite as 1 over cosine squared. And my cosecant I can write as 1 over sine. And then on my denominator, I've got 1 over cosine squared x and 1 over sine squared x. So whenever possible, I try not to have fractions, especially like fractions over fractions. That seems a lot. So the way I could get rid of my denominators is I've got cosines and sines. So I'm going to multiply the top and the bottom by cosine squared x, sine squared x. So with that, when I am simplifying, when I'm simplifying the top, I can simplify out the cosines, the sine squared, one of the sines will simplify. So on top, all I'm left with is sine x, because these went, and then this went with one of these. On the denominator, I've got to distribute this to both of them because of the plus sign. So when I distribute it over here, my cosines will go, and I'll be left with a sine squared x. When I distribute it to this side, my sines will simplify, so I'm left with a cosine squared x. This looks familiar. That should look like one of your identities, so this can turn into a 1. So we'll have sine x over 1, which is the same as sine x. So multiple steps, but eventually we get a nice answer in the end. Whenever I have two fractions subtracted or added, usually my first step after getting sines and cosines is I like to get a common denominator so I can put them together into 1 because that's easier to simplify. So to get a common denominator, I'm just going to multiply each one by the other's denominator. So I'm going to multiply this side by cosine x. And this side by 1 minus sine x. So on this side, I'm left with cosine squared x. The whole bottom is going to look like that cosine x, 1 minus sine x. And on the right side, if I distribute, I'm going to have a minus sine x and a plus sine x squared, or sine squared x. So from there, if I'm looking at it, I've got a cosine squared plus a sine squared. Even though they're separated, I can put them together. So those are going to turn into a 1. So I'm left with 1 minus sine x. And then we've still got the cosine x, 1 minus sine x. La-di-da, the top and the bottom share something. So I can simplify these. So I'm left with 1 over cosine x. And I would leave it like that, because usually you want things in terms of sine or cosine. Boom, done. So I know not all of this is intuitive and sometimes it's hard to see, so I would just play with it for a while, see if you can find any patterns, rearrange things, try to get parts to match so that you can simplify them. That's all you can really do. And then the last part of the warm-up, so solve for x in the interval 0 over 2 pi. So we did a similar one of this in the other notes, so I could add over the 1, divide by 2. So cosine x equals 1 over 2. Cosine x is positive in the first and fourth quadrant, so that's pi over 3 and 5 pi over 3. If it had not given me this restriction of 0 to 2 pi, say if it had said, if we want all the solutions, then you would want to look at the coterminal angles to these. So coterminal means we're going to be adding or subtracting 2 pi. So for pi over 3, you'd be adding 2 pi k times, and that just means however many times you want to do it. If you want to do it 2 times, you multiply by 2. If you want to do it 3 times, multiply by 3. So k is just where you would plug in however many coterminals you want. Same with the 5 pi over 3. You would just be adding 2 pi times k. So that'd be if we want all solutions, and they didn't limit it to a 0 over 2 pi. All right, from here there are 9 problems. That last year I did as like card activities around the room. This year I'm going to do 4 of them with you, and then I want you to finish the other 5 on your own. And then my notes are online, so you can always check your answers there. I'm going to start with number 2. So solve for x in the interval 0 to 2 pi. So talking through how I would approach this, I see a squared, I see they have cotangents in common, so I'm going to try to move everything to the same side to start with. So I'm going to subtract over cotangent. I'm going to have cotangent x, cosine squared x, minus cotangent x. So from there I can see these both have a cotangent, so I can factor out a cotangent. So I've got cotangent x times cosine squared x minus 1 equals 0. And now we can just split the 2 parts up into both equaling 0. So I'm going to have cotangent x equals 0 and cosine squared x minus 1 equals 0. So if I solve those 2 separate parts, where is cotangent 0? So that is where x is at pi over 2 and 3 pi over 2. And here I can move over the 1, so I've got cosine squared x equals 1. Oh, actually, that's not how I approached it last time. I think this way will still work. The creative way I approached it last time was I said that this equals negative sine squared x, which if I simplify that, I could divide by a negative, take the square root, so your sine x is just going to equal 0. I'm pretty sure this would have worked the same way if we'd done it with the cosine. That's okay. So where does sine x equal 0? At pi and at 0. However, if I were to plug these back into the original, where is cotangent undefined? Cotangent is undefined at pi and at 0 because you'd get a 1 over 0 situation. So pi and 0 do not work as answers. So these are your only solutions. So especially with cotangents and tangents, you have to make sure that your answers actually fit the original equation. That was the trick on this one. All right, let's skip to number 4. So on number 4, this looks pretty wonky. So I'm going to use that useful u substitution again. So I'm going to say u equals sine x. And I'm going to plug in that u for sine x. So I'm going to have secant of u equals 1. Secant I could rewrite as 1 over cosine of u equals 1. So what would this u have to be for this whole thing to equal 1? Well, cosine equals 1 at 0. So that means your u has to equal 0. So if we wanted to finish solving this to solve for x, If u equals 0, then we could plug that in here for u. So I'm going to have 0 equals sine x. And where does sine x equal 0? X equals at 0, at pi. This one specifically says find all the solutions to the equation. So that means those coterminal angles again every time that your graph's going to hit at a 0 or a pi. So that's happening every pi. So this would be a pi times k. So k would just be however many times you want to multiply it. So these would be your answers. All right, let's go to number 6. So write the expression square root of 25 plus x squared as a multiple of a basic trig function given that x equals this. Well, they told us what x is, so we can plug this in for x. So that's how I'm going to start. So I'm going to do square root of 25 plus 5 tan theta squared. So with that, I could square this. So I'd be left with 25 plus 25 tan squared theta. They have a 25 in common, so I can factor that out. So I'll have 25 times 1 plus tan squared theta. Since these two parts are being multiplied, I could separate them and take the square root of each of them separately. So you can take the square root of 25, that's just 5. So we have 5, 1 plus tan squared theta. 1 plus tan squared theta is something we know. That is one of our identities that equals secant squared. So I can change this into a secant squared theta. And now this is something I can take the square root of. So that's going to be 5 secant theta. But the trick to this problem is, you know how normally we have like plus or minus square root? Well, this time they only gave us a positive square root. So that means we only want positive secants, because secant can sometimes be negative, sometimes be positive. Since they only gave us a positive square root, we want positive secant. And the only way to ensure that is to do absolute value of secant. So we're doing that because we want to keep secant positive. The last one I want to do as a group is number 8. So I'll go to number 8. So for number 8, we're going to use our calculator in degree mode. So make sure you go to mode degree, or however the inspires do it, to solve for all possible values of x. So we've got cosine x equals negative 0.7. So what we're going to do is in our calculator, we're going to do inverse cosine of negative 0.7, and that's going to tell us our angle. So when I do that, I end up getting 134.4. So something to note on this is that cosine equals negative values in 2 different quadrants. So with our all students take calculus, cosine is going to be negative in this quadrant and in this quadrant. So what I just found was 134. So 134 exists like around here. But we also need to account for it here. So that means we need to have an angle here, which would make this negative 134. So for our value for our degree, we're going to need plus or minus 134.4 degrees. If we wanted to account for all possible values of x, those are just 2 of them. We once again have to consider those coterminal angles. So every 360 degrees or every 2 pi, that's going to happen again. So to that plus or minus 134.4, I'm going to add, since we're doing degrees, I'm going to do 360k. So that'll give you your coterminal angles at both of the positive and the negative 134. So those would be all the possible times when cosine x could equal negative 0.7. So the other one, let's see if I can get this to work. So for sine squared x, I would start with taking the square root to get rid of the squared. So we're going to have sine x equals plus or minus square root of 0.4. So this is sine is positive and negative, so that's